So, so let's continue down the bullets I was hoping to cover. The next is how fast can we apply how can we come up with a JL embedding that's fast, where we can embed points quickly? So the original proofs of JL, all the proofs of JL really go through distributional JL. And as you saw with distributional JL, the distributions that people use are random dense matrices like IED plus minus ones, IED Gaussians, sub-Gaussians, or projection onto a random subspace. How do you actually do projection onto a random subspace? Well, one way to get a random subspace is like pick a bunch of random Gaussian vectors and orthonormalize them using Gram-Schmidt, right? But that's again still a random dense matrix. So multiplying by, doing your actual embedding is dense matrix vector multiplication, and it's an unstructured matrix. So this is not particularly fast. The running time is going to be m, the target dimension, the number of rows of the matrix, times what I call the zero norm, which is the support size of the vector x. So can you go faster? And the first paper that got asymptotic speedup, actually there was already a paper that got a speedup by a constant factor, by a factor of about 3. But the first paper that got an asymptotic speedup was by Jelani and Chazelle in 2006. And let me first, before I tell you what they did, let me tell you, I guess, how they thought about it. So the starting idea was the following. If I have a vector x and I'm trying to do dimensionality reduction, let me create a vector y, which is a sampled version of x, right? What do I mean by that? I mean, I just sample IID entries from x over and over again, m times. And I can express that as matrix vector multiplication in the following way. I can have a sampling matrix capital S, where each row just has a 1 in a random location and zeros everywhere else. So S times X is basically my sampled coordinates from X. Okay. Then the nice thing is that this has the correct expectation. If I look at the expectation, maybe I'll multiply S by 1 over m, or 1 over root m. Then the expectation of the norm squared is correct. It's what it should be. The problem is that this is high variance, right? So remember now, in this picture, the number of rows of the matrix is basically the number of samples I'm taking. So I would like to take as few samples as possible because then I'm doing dimensionality reduction into few dimensions. But I have a problem if I have high variance. In particular, what if my vector x is such that it's all zeros in every coordinate except 1 in one coordinate? Then unless I sample d coordinates from x, I'm probably not even going to see the non-zero. So I'm probably not going to preserve the norm. Yeah, question? So the question was, does this require that x is sparse? Well, this statement, the statement that the expectation is correct, doesn't depend on anything. X can be anything, and that will be true. The problem about high variance, that depends on what x is. For example, if x is the all ones vector, there's no variance. You can take one sample and it'll always be correct, right? But if x is a sparse vector with like all its mass concentrated in one coordinate, that's really bad. You're going to need d samples before you see anything interesting. So yeah, so the problem with this approach is that if you want it to work no matter what x is, well, in the worst case, x could be fully concentrated in one coordinate, so you would need more than d samples. Right? Yeah, that's true. The embedding is really fast, but the identity map is also really fast. So so that's not really super useful. I want the embedding to be fast and the dimension to be low at the same time. Okay, so the fix of Jelani and Chazelle is to borrow an idea from physics, namely this Heisenberg uncertainty principle. Okay, so what does the uncertainty principle say mathematically? It really says that if you have a vector x and you have its Fourier transform, x hat, they cannot both be concentrated in a few coordinates. In particular, if you take the vector x, which is all zeros but a 1 in a single coordinate, its Fourier transform is basically 1 over root d. The magnitude is 1 over root d in every coordinate, so it's like perfectly spread out. Okay. The opposite can also happen. It can be perfectly spread out. You take its Fourier transform and it collapses to 1 frequency. So version 2, instead of letting the matrix just be S, which is the sampling matrix, I'll let the new matrix be S times F. where f is the discrete Fourier transform. And that, the discrete Fourier transform can be multiplied by quickly. That's called the fast Fourier transform. And then S can also be multiplied by quickly, so I can compose them and have a fast algorithm. So I guess I flashed it, unfortunately. So, I mean, there's a problem with this, which is kind of the opposite problem. Namely, I want this S of x to work no matter what x is. But what if x is actually perfectly well spread, right? Then f will collapse it to a single frequency potentially. And then now I have the same problem now, where sampling is not going to see the mass unless I sample all the frequencies, right? Or unless I sample a linear number of frequencies. So I have a new problem. And in fact, you can have like both problems simultaneously roughly. It's possible to construct a vector which has square root of d non-zero entries that are equal mass on these square root d non-zero entries, and then all the rest are 0. And then its Fourier transform also is focused on square root d entries. So, I mean, yes, square root d is sublinear, but like I'm not just trying to get sublinear. I'm trying to get the JL bound, which is 1 over epsilon squared log 1 over delta, right? So it's kind of, there are vectors where neither SF nor S works great. So Ilon and Giselle did the following thing. They let their matrix pi be the product of 3 matrices, S times F times D. In fact, it was in the original paper has P times H times D, where H is like the Hadamard matrix, and P was a random sparse matrix. And it's because it was in his PhD thesis, so it's spelled PhD, I guess. So what you can show is that now D is a random matrix. It's a diagonal matrix with plus minus 1s on the diagonal. And what you can show is that no matter what X is, whether it's sparse, dense, in between, doesn't matter, with high probability over D, f dx is well spread. It has roughly 1 over root d mass in every coordinate. And roughly 1 over root d mass in every coordinate. And then once f dx is well spread, you condition on that event, and then now sampling works, because sampling works when things are well spread. And the end result is that you can actually embed x to f of x in d log d time using the fast Fourier transform. Okay. In reality, they don't get exactly d log d, they get d log d plus m cubed. And the reason is that this f dx thing doesn't perfectly spread the mass. It spreads it almost perfectly spreads the mass. There's some slop, right? It's not the case that everyone is going to be 1 over root d in magnitude. There's going to be some deviation. And because of that deviation, you do need to oversample a little bit, okay? So you don't get exactly the right JL bound. But you do that, you'll oversample a little bit. And then what you do is at the very end, you then apply JL to get the slow JL, the dense JL, to that vector to then finally get it down to the right dimension. But now you're doing the slow JL over like much smaller dimension than the original dimension, so it's not as slow. And that's kind of the source of this m cubed, is that final step where you're applying this dense JL in the low dimension. Okay. So it's much better than dense JL, but there is this thing here which is like an eyesore maybe. So there were people who worked on trying to get that m cubed down, and there were a bunch of follow-up works that basically could get rid of the m cubed. Okay, and really try to truly get d log d. Okay. Now, even this though, there's a downside, and I should mention there's still some open problems here. So basically, the best of these papers, if you really, really want to completely get rid of the m cubed, then your target dimension won't be 1 over epsilon squared log n. I think it'll be like 1 over epsilon squared log n times poly log n. Like there's a little extra slop there. But that's kind of where we're at right now. If you don't want to have that extra slop, you can definitely replace the m cubed with m squared. There's a paper that does that. But even if you got the d log d, there's another downside, which is that it's slow to embed sparse vectors. Basically, the running time, this d log d, okay, let me just put it like this. Forget about the math for a second. Let's just think about what I just said. Okay? What I just said was, if your input data is sparse and its mass is in just a few coordinates, that's bad for how the embedding works. So let's first smear all the mass everywhere and then sample. But that's bad for efficiency, because if my data is sparse, I would hope that computing on it is fast because there are very few coordinates that matter at all. But like I ruined that sparsity in step 1 by smearing the mass everywhere. So you could ask the question, okay, is there another approach that is faster when the data is sparse, such that I don't smear the mass over all linear number of coordinates? And one way to embed fast for sparse vectors, it also is faster for dense vectors, but if it's really dense, then the F of t is faster. But one way to get speed up is to make pi sparse, right? Like if pi is a really sparse matrix, then you can multiply by it quickly as well. And one matrix that people can show works, which is sparse, is the so-called count sketch. So the count sketch is a matrix that looks like this. Okay? So it has m rows, but you divide the m rows into s blocks. S is a parameter with s blocks of size m over s each. So m over s rows here, m over s rows in that block, m over s rows in that block, s blocks total. Each column has a plus minus 1 in a random location, normalized by root s. And the rest of the block is 0. So just as you see in the picture. And notice that you can map x to pi x. You can do matrix vector multiplication in time. Instead of m times the support size of the vector, s times the support size of the vector. You can do that. So one thing I showed with Daniel Kane is that if you insist on having the optimal JL bound, which is 1 upsilon squared log n, even then you can actually sparsify pi asymptotically. The naive thing would be that s is m, right? The naive thing would be that, well, your blocks only have 1 row each. That's basically just a dense matrix. We can make it so that s has epsilon times m. S is equal to epsilon times m. So basically, there's a block of 1 over epsilon coordinates, another block of 1 over epsilon coordinates, another block of 1 over epsilon coordinates. And in each block, there's only a single non-zero, and the rest of the block is 0. Which means you can sparsify the matrix by an epsilon factor. You can speed up your embedding time by an epsilon factor. Okay. And I stress that this is like for free, right? You're not losing anything. You're getting the same target dimension as JL. It's just faster. And we can also show a lower bound that if you want m to be the JL bound, this s is almost necessary, up to a log 1 over epsilon factor. You really do need s to be at least epsilon m over log 1 over epsilon. That log 1 over epsilon is like it's an open problem to remove it. And there's a chain of work to get down here. People could get, let me skip this for now. But let me say a little bit about how to analyze sparse JL, because it uses a tool that you've seen already, which is, you remember this, right? You remember when we were using the Hansen-Wright inequality to analyze the dense JL. I said that pi z is bz sigma. I can write down what bz was. We had our quadratic form. We used Hansen-Wright. So I can do the same thing again. I can say, well, we again have a quadratic form. It's just that the matrix bz has changed. So basically, for the sparse JL matrix, let eta ri be an indicator random variable for the event that pi ri is not 0. Okay. Then in the ether of bz, I can replace z transpose by introized product of eta r with z. So instead of z transpose, it'll be like eta1 dot z transpose, eta2 dot z transpose. Dot is introized product. And then the same thing is true. Pi z, where pi is the sparse JL, will equal this new bz times sigma. So again, I have my quadratic form. And I can just do Hansen-Wright as before. It's a little bit more complicated because now my matrix B is a random matrix because it depends on eta. Right? It depends on where my non-zeros are. That's a random decision. So BZ is a random matrix, which means this middle matrix AZ, BZ transpose BZ, is a random matrix. So its Frobenius norm, for example, is a random variable. So when you apply Hansen-Wright, you have to somehow take care of that, but it's doable. Okay. Okay, good. A few more things. Isn't storing the random matrix expensive? Okay. I mean, why might that matter? You can imagine that if I have some kind of distributed application where you have a subset of the vectors, I have a subset of the vectors, and we're trying to compute something jointly and then communicate intermediate results to aggregate or something like that, then if in the pre-processing step, we're going to pick a random embedding. We need to make sure we're all using the same random embedding. And then I might have to communicate that. And if pi is a big random matrix, telling you what pi got picked is basically I have to send you like MD numbers over the wire, right? So ideally, I would like pi to be chosen in such a way that it has a very succinct description so that I can communicate it using very few bits. Or if I have a low memory algorithm, I want to be able to store pi using very few bits. And isn't storing a huge random matrix expensive? Remember, D is huge, right? So M times D is huger. Okay. So how do you represent pi space efficiently? So as we've seen, in the first paper that proved it was Akleoptis, the entries of pi could be Rademachers, plus minus 1, right? Plus minus 1 over m. So that already tells you can use M times D random bits, right? The entries are not Gaussians, they're just bits. They're just plus minus 1s. So M times D bits. Clarkson and Woodruff showed that, in fact, the sigma ij's, the entries, don't need to be independent. They can just be k-wise independent, where k is log 1 over delta. People familiar with like k-wise independence? Okay, maybe some fraction of the people. So okay, so I don't think I have time to really get into it, but basically, what k-wise independence means is, so you have a collection of random variables. Okay, if you just look at any k of them at a time, those k, and you look at the marginal distribution on those k, that marginal distribution on those k looks as if those k are fully independent. But if you look at all n random variables at the same time, they're not all independent. Okay, and the nice thing about k-wise independent distributions is that you can generate these big vectors of random variables using many fewer than n bits. So like if you wanted n random bits that are only k-wise independent, turns out you can get away with something like k log n bits. So like scales linearly with k as opposed to with n. So Clarkson and Woodruff said they only need to be log 1 over delta wise independent, where delta is the failure probability in DJL. So the total bit complexity of storing pi is k log n. N is the number of random variables you need, which in our case is m times d. So it basically is like log 1 over delta times log d bits. And you can do actually even better, and this is something we saw in 2011. There's a way to basically choose pi as being the product of matrices that have fewer and fewer rows, such that you use more and more independence the fewer rows you have, and do some kind of balancing and get fewer random bits at the end of the day. I'm not going to show the details, but kind of the record construction is it's possible to come up with a distribution d epsilon delta. Remember, d epsilon delta is the distribution over matrices, such that you can sample from the distribution using only this number of bits. And there's a belief that this should be possible, log d plus log 1 over delta, without this extra stuff here. And that's still today an open question. It's a de-randomization question of whether or not you can get away with these few random bits. What can we get for specific applications and instances? Okay, so now let me talk about like some applications of JL and how you can sometimes do better than just applying JL in a black box way. So one technique that's very popular is sketch and solve. What is sketch and solve? Sketch and solve is, I guess, it's supposed to be as the name suggests. So I have some problem that I'm trying to solve. Think like an optimization problem. K-means clustering, low-rank approximation, regression. And the idea is I just take my data, I apply the embedding to my data, and then now I run my algorithm on the lower dimensional version and solve it. And then I'll just use that as my answer for the original problem. Okay. So I mean, you'll see some examples of what this means. But you can do it for like some large-scale linear algebra problems, like least squares regression, principal components analysis, even matrix-matrix multiplication. What does that look like? So for example, let's say least squares regression. So beta least squares is the argmin of, so okay, what's your input? Your input is a matrix X together with a vector Y, and you're trying to find a beta to minimize the L2 norm of X beta minus Y, right? So what does sketch and solve say? Instead of minimizing the norm of X beta minus Y, I'll minimize the norm of pi X beta minus pi Y, where pi is my dimensionality reducing matrix. Okay. Or for principal components analysis, I'm trying to find a rank K projection P star that minimizes the Frobenius norm of I minus P A Frobenius norm squared, right? So, so what does that mean? I mean, so I minus P times A is A minus PA. So PA is my my low rank approximation of A, right? So I want to find a low rank version that is as close to A as possible under some norm, say Frobenius norm. So the sketch and solve version is, so A has some number of columns. I'll shrink the number of columns by multiplying on the right by pi transpose. So now my new matrix that I'm trying to solve for is A pi transpose, and now I want to find a good projection for that. Matrix-matrix multiplication, I want to compute A transpose B. I'll instead compute pi A transpose pi B. Right. So like these are examples of sketch and solve. You can show that if pi is chosen appropriately, you get good things like your error, your regression error is at most 1 plus epsilon times opt. If you do sketch and solve with the appropriate parameters. Similarly, you get something like that for low rank approximation. Also, you can bound the error. So like what you actually wanted was A transpose B, call that C. Instead, we'll compute a C tilde. And you can show that C tilde is close to C under some norm with sketch and solve. And what sketching matrix, what kind of sketching matrices can you choose? You can choose like ID sub Gaussian, or you can choose S times F times D. Just this is like the Ilon Chazelle kind of fast JL. You can use count sketch like Sparse JL. Okay. You probably don't want to use the first one. Like for JL, I mean, using a dense random matrix for JL is not ideal. There are faster things like Sparse JL or like fast JL. But dense JL is still useful. It's just not as fast as possible, right? I claim that for a lot of these problems, using pi to be a dense sub-Gaussian matrix is actually useless, okay? And the reason it's actually useless for a lot of these problems is, like for example here, I need to compute pi times x. But like, this is now dense matrix-matrix multiplication, which is really slow. And you know, with the parameter, I haven't shown you what the parameters are, but basically the parameters are going to end up being such that doing this dense matrix-matrix multiplication is slower than just solving the original regression problem anyway. So you really do need like the fast JL or the sparse JL for this to even make sense. But once you do that, it does make sense. So let me just show you an example of like why sketch and solve works for regression. So let's say that, so definition, for a d-dimensional subspace of Rn, we'll say that pi is a subspace embedding for that subspace if it preserves the norm of every vector in the subspace simultaneously. Notice that this is like an infinite JL, right? JL says I'm a finite set of vectors, I preserve their distances. This is not a finite set of vectors. This is an entire subspace, which is infinite. You can use JL to come up with subspace embeddings because what you can do is you can basically say, let me take a finite epsilon net of the subspace. And now with JL, I can preserve that epsilon net. And then I can use some argument to say, if I preserve the net, I preserve everything. There's some way of doing that. But you know, you can actually sometimes do better by just directly proving this without going through JL. And now the claim is that if pi is an epsilon subspace embedding for a certain subspace, namely the span of the columns of y as well as the columns of x as well as y in the regression problem, then if B tilde is the solution to sketch and solve, it's almost as good as the actual optimal regression solution. And why is that the case? Well, here's the proof. It's a very short proof. If I look at this is the error, this is the regression error for the sketched version of the problem, the lower dimensional version of the problem. That error has to be less than the optimal error for the original problem. Why? Because beta tilde is the opt for the sketched version, for the lower dimensional version. Okay? Okay, good. And now I can write this as pi times a certain vector in that subspace. So its norm is preserved, right? And similarly, I can write this as pi times another vector, so its norm is preserved. And then now I can just move things around. I'll take this and divide by 1 minus epsilon and divide by 1 minus epsilon here, and I get exactly what I said. x beta tilde ls minus y, norm squared is at most 1 plus epsilon over 1 minus epsilon times the right-hand side. I think I'm basically out of time, so maybe I'll talk for like 1 more minute. One way, how do you obtain oblivious subspace embeddings? One way is to use JL over a net, as I said. Another way is to argue directly about that, the fact that you have, argue directly and show that you have a subspace embedding with high probability. Let me skip that. Another application that's interesting is K-means clustering. What is K-means? Given a parameter K, which is a positive integer, and a collection of points you want to cluster, find cluster centers, minimizing the sum. Yes?
Actually, I was wrong. We have at least 5 minutes according to schedule.
5 more minutes?
5 more minutes.
Oh, 5 more minutes. Okay, okay, good.
Yeah, so if you need it.
Okay, so I'll target 12:10 then. Okay. So, and then the cost of a choice of cluster centers is the sum of square distances to the closest center. That's K-means clustering. So like find cluster centers that minimize this cost. Okay. Now, any cluster induces a K partition on the points. Namely, all the points that are closest to Y1, that's cluster 1. All the points that are closest to Y2, that's cluster 2. And for any choice of the Ys, and then I want to say, so any clustering induces a partition, and then once you have the partition, you could say, what is the best choice of Ys for this partition? And it turns out the best choice of Ys for the partition are the centroids, namely, just take the average vector in the partition. So look at the sum of all points in the partition divided by the size of the partition. And then now the cost of the partition is the sum over partitions, sum over points in that partition, squared distance between that point and the centroid. And if you just do some rearranging, which I'm not going to do on the slide, you can show that this is actually equal to this summation. Sum over j, sum over partitions, 1 over the size of the partition, sum over pairs of points in the partition, distance squared between the pair of points. So the nice thing is that the cost of any clustering in K-means clustering only depends on square distances within the original point set, which means if you preserve distances within the original point set, you preserve the cost of any clustering, which means you can do sketch and solve for K-means, just using JL as a black box, which means you can get away with dimension 1 over epsilon squared log n, right? That's just JL as a black box. Okay. But this is an example where even though you can get something with JL as a black box, you can do better by analyzing random projections tailored to your problem. So there's a better argument for dimensionality reduction for K-means. In particular, this paper by Boutsidas et al. Showed that you can reformulate K-means as a constrained low-rank approximation problem, basically constrained PCA. Why? So imagine that these are my 4 points that I'm trying to cluster, and I decided that I want to cluster them in this way. This is my partition. 1, 2 go together, 3 goes together, 4 goes together. For that partition, I can define a matrix XP, which is like a point cluster indicator matrix. So so it's basically an n by k matrix, where the ijth entry is 0 if point I is not in cluster J. And if point I is in cluster J, it's non-zero. And specifically, it's going to be 1 divided by square root of the cluster size. Okay. And then now, XP, notice, has orthonormal columns. I mean, the columns are clearly orthogonal because they have disjoint support. A point is only in one cluster. And because I normalize by square root the size of the partition, they also have unit norm. So XP has orthonormal columns, which means that XP transpose is a projection matrix. And in particular, if you define a matrix A whose rows are the vectors that you're trying to cluster, you can prove to yourself, if you just reason about what this is doing, XP transpose A, its ith row is the centroid of the cluster that the ith point belongs to. So basically, XP transpose A is a mapping of each original point to its cluster center. Which means that if you look at A minus XP transpose A, that's a matrix whose ith row is the difference vector between the ith point and its centroid of its cluster. which means that the Frobenius squared of this matrix is exactly the cost of the partition. Okay? Which means that if I define a certain set of orthogonal projections, if I define Q to be the set of all matrices XP transpose where P is a K partition, I'm trying to find the optimal Q, the optimal element of Q to minimize this cost. This is exactly a constrained low rank approximation matrix, constrained low rank approximation problem. Find Q op, which is the arg min over all Q in script Q of A minus QA for Frobenius norm squared. So basically I constrain Q to be in script Q as opposed to being an arbitrary orthogonal projection of rank K. And then now I can try to do a discussion solve where instead of minimizing this, I minimize I minus Q A pi transpose. So I basically sketch down the columns of A. Right? Remember A, the rows of A are the points to be clustered, right? So A is an n by D matrix. So now it's an n by M matrix. So the points now are M dimensional. So I've reduced the dimension. And it's known by this paper by Cohen et al. That to optimize this up to a 1 plus epsilon factor, it suffices for pi to embed into only K over epsilon squared dimensions. If you embed into K over epsilon squared dimensions, you'll actually preserve this Frobenius norm squared for any Q that is a rank K orthogonal projection. I'm not going to show you the proof, but it's true. And notice now this doesn't depend on log, it doesn't depend on n. JL depends on n, it's log n dimensions, right? This is K dimensions. What's K? K is the number of clusters you want. So if I only want 5 clusters, my dimension depends on 5. It doesn't depend on the number of points to be clustered. And in fact, it was later shown that specifically for clustering, not for all rank K projections, but for clustering, you can actually get away with roughly log K dimensions. And of course, K is always less than n. Right? K is the number of cluster centers. Yeah, so I think I am actually out of time. There was one bullet that I didn't get to, and there were some other things that I didn't get to either, but that's okay. I think I've shown you enough stuff for the day. So let me just pause here and ask if there are any questions.